Now in this video I want to explore sine and cosine functions using the matplotlib's graph library a little further. So let's create a t-array using linspace from 0 to 2 pi, numpy pi. Let's have 20 points between them, and my function will be numpy sine t. So save it and then run the simple script, and let's have a look what t array looks like. That's the t array from 0 to 2 pi, 20 elements, and the sine values corresponding to them. Plotting the function plt plot t versus y will show us the sine graph. The graph is a little bit rugged on the maximum and minimum values. I can make it more smooth here by increasing the number of points there. So run it. Now we have a better, nice, smooth sine curve. This is the corresponding t values, this time 50, and their sine values. Okay, so let's look at the graph once more. Okay, I want to look at different aspects of the sine, still very fundamental aspects of the sine curve with another sine as well. I want to add another sine to my graph. So let's say this is y1, and it's the second sine signal. So here is the first plot, and then this is the second one. Okay, because I have exactly the same sine curves, they are on top of one another, so I see only one. Now let's begin first the phase vector. So let's say phase 1 and phase 2. So let's say the phase of the first curve is 0.5 and the next one is 0. I add the phase, this is here, inside the sine function, phase 2. I have two functions, so it will be better if I show the functions with different styles. So the first one is the connected or the smooth line. The second one is dashed lines. So let's have a look. Okay, let's spend a little time to see to explore what we see. I have two curves. Both of them are sine curves. However, the first one has a phase shift, a positive phase of 0.5 radians, and the second one has a 0 phase. Therefore, these two curves do not coincide. But the first one is ahead of the second one. How much? By 0.5 radians. Okay, so if I increase this to 1, for example, 1 radians, then this first curve will be even more ahead. At t, what do I mean by ahead? At t equals 0, the first sine signal is already accumulated values of more than 0.75. The next one will get to those numbers only after about 1 in time 1 points. 1 radian seconds, in other words. Okay, so phase changes, phase makes the signal, shifts the signal in time. In fact, if I phase shift this by pi over 2, I get a cosine function. So a sine function with a pi over 2 phase shift is actually a cosine function. If you want to convince yourself, change the second one to a cosine and then they overlap nicely. Okay, so come back to the sine with a sine, so a phase factor. So cosine and cosine are basically the same functions with a phase factor. Now let's discuss the amplitudes. Amplitude 1, this time I write the amplitude outside the functions, amplitude 2, and amp1, amp2. Let's say the first function is the amplitude 2.0 and the next one is 1.0. So let's run. With these amplitudes, I expect the first signal to be twice. So the maximum is 2 and the minimum is -2 for the first signal. And this is my second one. The first signal is still with the phase shift as well. So amplitude only changes the maximum and minimum of functions, of the sine functions. Next, I would like to see how a bias factor shifts. Again, I would give, for example, a 3 bias to the first curve and a 0 to the next one. So let's run this. I must have the bias here, so bias 2 basically shifts the curves. There you have the first curve shifted up by 3. The next one is still around 0. Next, I want to do the frequencies. So let's have 2 different frequencies for each signal, frequency 1 and frequency 2. This is where I define the frequencies, frequency 1 times t and then frequency 2 times t. Let's have the first function again, twice the frequency of the second one. And let's see how this makes a difference. When I run the small script, it shows that the first wave is now twice the frequency of the second one. In other words, in the same time period, when the second wave or second function makes a full cycle from 0 up and down and back to 0, the second one makes 2 cycles, up and down, up and down. So this is the effect of frequency visualized. So let's make the frequency of the second curve 5 and the first one still 2. Let's see. Okay, I can. Now this is a higher frequency and that's a lower frequency. And that's the amplitude. We discussed the phase and the bias. So let's repeat that by first getting rid of the bias. I make the biases equal, so that will bring the second curve back around 0. Still the amplitude is 2, so let's decrease that amplitude to 1. there. Now the same amplitude, still the frequency are different, 2 and 5. So let's bring them back to the same frequency. Okay, and now removing the phase factor, making it 0, will make these two waves the same wave. Okay, at this point let's repeat what we've done. We investigated phase, amplitude, a bias, and the frequency of a sine wave. In the next video, I would like to discuss a phase space representation of these two curves. Okay, let's continue from where we left. Now, I investigated the representation of as two sine curves and their frequencies, phases, amplitudes, etc. Now, I want to plot the same two curves in a different representation. So let me run this. So when I have two curves coincide, this is how plots with respect to time. So y-axis is my signal, and then x-axis is the time. So instead of plotting it this way, I want to look how it looks like if I draw y1 versus y2. Now y1 is of course my sine, and y2 is the other sine. I want to plot y1 versus y2. So y1 is on the x-axis and y2 is on the y-axis. So this is how it looks like. It looks quite unexpected. A curvy sine line looks almost a linear line. So let's have a look at the data points to have a better idea of what is going on here. So these are the data points. It's better to plot them this way. So I have more data points on this side and more on that side. Before I do anything, I want to bring something to your attention. The axis goes from -1 to 1 and -1 to 1 there. However, this is not a square. It looks like a rectangle. To make these representations more intuitive, I would like to make the aspect ratio of this square rectangle equal. So this is how you do that. Before you plot, if you say figure and axis plt subplots, and then axis set aspect 1. So this will make your okay, these two lines are not obvious at this point, and I don't want to go into detail there. Just add these two lines and then see the result. Okay, now we have a square -1 to 1, -1 to 1. So this is a square, not a rectangle anymore. Therefore, the aspect ratio, aspect of y with respect to x, is equal to 1. And this is what I want. Okay, so here is my second representation. And I still want this plot ty1, ty2. So this is my two signals on top of one another, and then this is the new representation that I just introduced. Now let's explore by changing the phases, etc. How about we start by changing the phase of the first signal to pi over 2. Remember, this phase will make the first curve a cosine, and the second one still will be a sine. So we have a cosine and a sine. There we will see the difference on the line plot and on this phase plot. Next, let me run, and so this is really interesting. This is the cosine, and it's the sine functions, and this is a full circle that we have. Now remember, when the phase vector was 0, the lines were on top of one another, the curves were on top of another, and then this phase plot was a straight line. So changing it to pi over 2, I have a sine and a cosine and a full circle. It's interesting. At this point, let's do a different phase. Instead of not pi over 2, how about we have a 0.5, and then look at the graphs again. Okay, then we have a slight phase change over there, and on the phase plot I don't have a complete circle but an ellipse like shape on the phase plot. If you have a minus phase, then you still have the same type of, and this is something I was expecting it to move the other way around, but never mind, it's okay. So let's do the pi over 2 phase again. That's my circle. Okay. How about we change the amplitude? So in which way does it affect? So let's make the amplitude of the first wave again twice, and then run it. Okay, so here is your first wave, twice the amplitude. And remember, I put the first one on the x-axis. So this is an ellipse that has the major axis twice the minor axis. Okay. How does the bias change the picture? Let me do a 3-point bias on the second curve. In other words, I am moving the second curve by a magnitude of 3 towards higher values. So this is what it looks like. Now the only difference is, now your ellipse is, the origin is 0 and 3 here. So the ellipse moved up because I gave a phase shift, a bias to the first curve. Okay, maybe the most interesting is how the frequency affects my phase plots. So let's make the first curve twice the frequency. Okay, the picture changed completely. Now I don't have a closed curve. What about making it 3? That still further gives really something unexpected. I have the curves rough on the sides, so now is the time to increase the sampling. Okay, nice. and smooth curves. I think I should take this away to make it look better. Okay, so that's the phase plot of two signals with different frequencies. If I change the frequency of the second one as well, okay, now that's a different curve, 3 and 2. Frequency is 3 and frequency 3, and if I change the frequency further, I will get different, and maybe let's conclude it with this one. Okay, so that's a different frequency plot of these two waves. I want you to think about the representation below. Now, if I take the bias off here, of course it won't change the phase plot, and if I change the amplitude, won't change the topology of the curve. Okay, still the same curve. Now my maximums are 1 and -1 in the both scales. So different frequencies give rise to a complex phase plot in the second representation, so making them back to 1 and then 1 here. Okay, so I have my circle, and finally removing the phase, we have this single line. I hope you find this interesting. That is a phase representation of two sine and cosine functions. In this video I will be doing 3D graphs. To be able to do 3D graphs, we need the following import line from MPL toolkits. Import matplotlib 3D. So once you import this, one more thing you need to do is to create an axis using the plot axis function, and then giving it as a parameter projection 3D. So with these two additions, I am now ready to do a 3D graph. So a 3D graph has x, y, and z values. So I want to do that using parametric descriptions. So let's first do a time array. Let's say our time array is linspace from 0 to 10, and then we have, say, 20 points. So time starts from 0 and goes up to 10. My x coordinate, let's assume this is a particle moving in 3 dimensions. X coordinate, let's say the x coordinate is a sine function. In other words, the particle is doing a harmonic motion in the x-axis. So it goes up to 1 and then comes back to 0 and goes to -1 and makes a harmonic motion here. So a sine, x is a sine function of t. So in this case, because t goes from 0 to 10, this particle will make more than 3 cycles. So more than a cycle. Remember, one period is 2 pi radians, so 10 is more than 6.28 we are talking about now of a cycle and a little more, but not 2 full cycles for the x coordinate. And then y, let's make this a cosine function. So in the y coordinate, again a harmonic motion. For the z coordinate, to make it easier, I would prefer to make it just a t. So the particle starts from 0 and goes up to 10 in the z-axis. Okay. So if I run this part, I don't have my particle over there, but I want to first show you the arrays. This is the T array. Maybe I can make this a little larger. T. It's the T array, X, Y, and Z. So I have X coordinates, Y coordinates, and Z coordinates of the particle, 20 coordinates corresponding to time. To plot it, X, I use the x's created here, X dot plot 3D, X, Y, and Z. Okay, let's run this. There is the projection or the trajectory, so rather the trajectory of my particle, starting from 0 and 1 and goes up. So this is the z-axis, so the particle goes higher and higher as time passes, and it makes a circular motion. So if you want to make the let's make the particle move the circular frequency a little higher and see what the result looks like. So the particle makes more turns as it goes up, but that doesn't look like a circle, and the reason is, of course, the sampling is too low to show that. So let's make this really high. So this is the nice circles that the particle traverses. So it makes circles and goes up. Okay, and then what do you think this will look like if I make the other one also a sine? So this looks like this is similar to what we see, the single line of the phase representation of a sine and a cosine. So this is not a circle but a line. It still goes up. I go back to the cosine part. Okay. If you are not happy with the ticks, you can change the ticks easily there. Then to conclude this, I can also say the z values, for example, how about make it an negative exponential. So think about this function. I am not going to plot it 3D yet, so let me run this part once, and then so this is your t and that is your z. If I plot t versus z, so it is an exponential decay from 1 to 0. So z value of this moment will go from 1 and slowly to 0, becoming the velocity becomes slower and slower as it approaches 10. So in this way, let's plot the 3D once more. So your circle begins here, and then the particle moves down, and then the z velocity is less and less, so the particle now moves in the circle down below here. Okay, let's stop here.